this is it. I think I'm ready for giving you a no maths explanation of Shor's algorithm. So I'll first a disclaimer. Just let me go back to the actual, because he has a. So we don't this. We won't sort of. I'm trying to find the. And I'm trying to find. I'm not gonna try to keep it short. I'll probably do a 2-minute version of it, but quantum computing series. So basically, what I want to do is the following. So there's a caveat to my no maths statement here, which is to be able to understand Shor's algorithm. There is a non-quantum part, which is basically actually quite mathematical. I mean, that's the reason it works is because of a mathematical trick, which means you can't really explain the full algorithm without understanding the mathematical representation that the algorithm does in order to exploit quantum computing features. So this is explained in here. I highly recommend you guys check out this article if you want to really dive into this, because it explains, I think it explains it fairly well. All that you need to know and all that we need to know for this explanation is exactly what is here, which is basically so you have to take that for granted right now for the video, which is basically if we are able to find that period. So you see that here it kind of repeats, right? So this is one, and then here's another one. So if you're able to find that period in here, which is like 1, 2, 3, 4, 5, 6, right? So it's here. So it repeats every 6. Then you are able to find the factors, so the prime factors, and that's because Shor's algorithm is to find the prime factors of a bigger number of a number. So, and let's assume this is true. To prove that, you do have to go through the maths, and that is something that you can't really you can't really avoid, because it's basically a mathematical trick. There's probably some analogies that can be used to explain that in a non-mathematical way, but the idea is that if you understand that, then it's good. But the way the quantum part works can be explained without all the mathematics, which is really my goal here. But I do warn you that if you haven't checked the quantum Fourier transform videos, go check them out, because it's it's one of the basic building blocks of the algorithm, which I'm going to really roughly explain just for you to get the full picture. But I think that's something if you want to take a look in detail. I also have a couple of videos that explain the quantum Fourier transform and its inverse without the maths. So go check them out. Now, having said that, let's get to it. So, in one of these articles, there's an actual overview. Exactly. So we're gonna be taking a look at this quite a lot. See if I can zoom in a little bit, because so this is how the quantum part looks like and works. Basically, you've got some pre-processing in here that helps you determine what gates you're going to be using to build that part. So this is important. So you do that not in the QPU, you do that outside, and then you've got some classical processing at the end, which basically allows you to then figure out really the prime numbers, just so you understand. But what this piece, the quantum piece, is doing is basically the goal of this is trying to find that period, right? So we'll focus on that, and then you have to, as I said, know if you are able to find the period, then you're able to find the prime factors. There's tons of materials out there that explain mathematically how does that work. So I'm gonna keep it out of scope for this, because I'm interested in the quantum part, which is I don't understand, because it's really, I think, fairly simple. Once you put the pieces together, it's a fairly elegant piece of circuit, and it's just, I think there's a lack of out there currently a lack of maybe willingness to explain things in a way that are not mathematical. So that's what I'm gonna try to do here. And as you see, there's the block here is the inverse of the QFT. Now, how does this work? So the idea is that the basic idea, let's start from behind. I think that makes a lot of sense. Is that if you're um, if you're able to encode, imagine that we would be able to encode these values 1, 2, 4, 8, 16, 11, right? Traditionally as sort of a wave, right? So you've got like this, and then you've got like 1, and you've got 2, and then you've got 4, and you've got like 8, and you've got like 16. So and if you kind of keep doing these, right, like you get that kind of waves, and then you would get the kind of repeating pattern. So if you would be able to do that, then that's exactly the input that the quantum Fourier transform needs to tell you what's the period. Like, I mean, what's the frequency in that case, right? Because that's what the QFT does. And go check that out, because the idea of the QFT is that it's just you encode these. Let me clean that up. You encode this wave into a superposition, right? So basically, you've got like so if you've got here your all the different possible values of your superposition, they all have the same they all will have the same probability of being measured, but each of them would have a phase which is slightly rotated, and because of that you will have different, like you would have that wave that I just draw will be encoded in the phases of the superposition. Let me see if I can show this, because I remember that I did some examples. Maybe I still have them here. Quantum Fourier transform, exactly. Maybe that still works. Because that was a quantum Fourier transform. There is some current example, QGAN. Because if I remove all that, because this is the actual quantum Fourier transform. So that's just to show you what I mean by encoding it in the Nickel superposition, right? So so here's an example. Exactly, here's an example where you kind of see that it's sort of a square wave in this case, right? So it's like these and these and these and these, but you would have those colors like slightly changing from blue to yellow in this case, and that would be a more smooth type of wave anyway. But you encode them like that, so you encode them in the phases of your different possible states. And once you have that, you apply the quantum Fourier transform, and then you get basically what the quantum Fourier transform is doing is kind of applying Hadamard's and applying rotations. It's a combination of Hadamard's and rotations in a way that you're kind of collecting all the information. So you're wrapping things up, and then you end up with something like these, which basically as an example, tells you that maybe if this is like 2 and this is like, I don't know, 6, that those are the two frequencies that this wave you've encoded here is made of. But again, just go check the QFT video. That's what it does. So and so this is really what this piece here is doing, right? So what the first part is doing here is basically let's see how I can explain that. So it's it's basically encoding the, let me see, just have to find an easier way to explain that. So first of all, you see here that the first step we have is we're preparing a superposition. So you're basically preparing the stage to encode your wave. The thing is, because the way you're going to encode the phase is by using an effect, a quantum computing feature that's called a phase kickback. So the phase kickback, I can show you quickly an example. There's an example of a phase kickback that it's simple to see. which I will show you because so if I go to Kindle, the Kindle thing, and then exactly here there's a face kickback, I think, effect. You can easily see here, face kickback. So I'm gonna try to do this. So those are control Zs. So if you have, let's say, I'll just do a new one. We'll just have 3 registers. We'll have 2 Hadamards, and we'll have a 1. I think it's needed for that. Exactly. And then you do like here and here. So maybe it's easier just to see with 1. Can we just see it with 1? Probably we can, because I think that example is really not needed. So good. So as you can see, they're all blue. So the face is the face of the qubits is the same. But once I apply a control rotation. Does this help me visualize that? How can I visualize the face? Because I think with this notation, sadly, I can't visualize the face of each separate qubit. I think true. But essentially what this is doing is it's changing the phase of both qubits. You can see that example here. So in here I have a more complex example. Let me show you. Because if you would apply, the reason you can say, if you would apply a rotation on the Z here, right? You see the color is different, right? You see, right, that the color is different. And so when you apply the control rotation, that color is different because here you've got the phases of both qubits playing together. That's kind of one way to see it here. If we go and do the same example, and we have these. So, and this is a quantum feature. This is basically one of the things that is super powerful, is that just because of the way the qubits interact with each other, that happens. And this is something that you can then use to our advantage. So the first one, I think what they do is so I'm trying to go back here. First one is a rotation of 45 degrees and then 90 degrees. So the first one is actually like this. And then this one goes here. And this one is on 90 degrees. So you see that it gradually, that's pretty cool. You see that it gradually changes, right? Here. So this is what you see in the book here by those phases that you can see here displayed. And this has happened in the register 1, like in these first 2 qubits, despite the fact that they are only used as control gates. So that's really an intuitive, right? But it's really a quantum effect that it's worth noticing, and that's exactly, it's called phase kickback. So this means when we are rotating the phase in a qubit that is on the state 1, the same phase gets kicked back to the controlled qubit, to the qubits that act as a control. And so this is a really cool way to encode. If you pay attention, we are really encoding a wave, so to say, right, in our superposition here. So this is really what this step here is doing. So if you pay attention to the nature of that, imagine that we would be able to encode these numbers, right, into the phase into our phases. So we would essentially at some point have an overflow, right? Because we're doing it's modulo 21, so you have a certain amount of qubits that you're using to represent that, and where am I? Here. So you have a certain amount of qubits that you are using to represent to represent the number that you're multiplying. The result exactly. So the idea is that you got to figure out a set of operations here that implement. So this box here implements your modulo like multiplication, because it's like 2 to the power of 0, to the power of 1, to the power of 2, to the power of 3. I mean, and here 2 is something that you've picked up randomly. It's kind of your input. And when you implement that, you do it in a way that the phase gets kicked back here in all the elements of your superposition that have a 1 in the lowest value. Then this phase gets kicked back in all the elements of your superposition that have a 1 in the second lowest value, and so on and so on and so on. So the effect this has is that you end up exactly with something that looks like that, but you've got like all your space here covered. I mean, actually, you've got your space covered because that's just like the part that you're losing because of like that's kind of your register 2 and that's your register 1. And you end up with that. So, and because you end up with these, then you're now able to basically run that through the QFT, the inverse of the QFT. So this is confusing. And in this book, and I've tried to address that in Twitter, but I haven't gotten an answer yet. In this book, they present the this is, by the way, a Programming Quantum Computers book, and it's really awesome, and you should really buy this. But there's something that's confusing me because I think they mess up a little bit with QFT and the inverse of the QFT. The algorithm talks about the inverse, using the inverse of the QFT, which essentially means the input is a wave encoded in your superposition, and the output is the actual set of frequencies. So yeah, and I think they use the opposite definition, so it's kind of confusing a little bit. But then they are contradicting themselves in the middle of the book, I think. I don't know, but that's the basic idea, and that's it. Really, that's it. Because once you have the wave, so it's kind of by multiplying this, and this really comes down to how you implement that. It really comes down to how you implement that. So the problem is there is a rather complicated. It's a rather complicated thing to do right now because you need a lot of qubits for these, even for smaller factorizations, and you need to do this efficiently as well. So it's I don't know if it makes, because what I want to probably do maybe what I want to do in the 2 minutes video is sort of prepare an actual example that is gonna help you understand better visually what's happening within the algorithm. But intuitively, that's what's happening. So the trick here is that each of these operations is leaving a trace, so to say. It's leaving like a footprint, and this footprint is the phase is being kicked back into your superposition, so you end up with a wave that's encoded into your superposition, which is exactly what the inverse of the QFT needs to actually do its job. So that's really that's really it. I mean, there's nothing else to, the whole algorithm is more complex, right? So you definitely go and read the actual mathematical part that's around the quantum thing, because that's what's going to give you the full picture. The idea is you pick an x, right, which is in this case here 2. You pick an x here, so x says 2, and then you basically come up with a priori the gates that come here, and then you run the algorithm. So by doing the multiplication with the gates, you're basically encoding the results into your superposition by moving the phases. And then you have those results proportionally rotated, right? And remember the phase, right? So you can think of the phase as being like so you've got a full rotation. So the idea here is that you have the number that you're going to get here as a result, say 6, right? It's not really the period. It's actually, what it's telling you is that it's a sixth of it's a 6. Sorry, it's a 6 over the maximum amount of the biggest number you can represent with that amount of qubits. So it's trickier than that. I think it's pretty complex to explain in a sort of a short time frame. But it's like, and so this is exactly. This is exactly, then you divide this by that number, and then you've got sort of the fraction, and that's your fraction of that rotation that you're getting, and this is then telling you kind of what's the cycle. Yeah, but I think I'll probably do an example that's maybe going to be more helpful, but basically that's the intuitive idea. Yeah, so just one more quick time of the quantum part. You basically prepare superposition, you do a multiplication, like the actual, these multiplications here, these operations, the the trace of those, like the results, get kicked back into your superposition, basically giving you a wave encoded, like a phase encoded wave. So you've got like an equal superposition, and then inside the colors here are kind of, like, of course that's crap, but like, you know what I mean. So the colors, the phases are encoded here, and then you basically run that through the QFT, and then you've got your answer back, which is exactly what's that frequency. Yeah, and that's basically it. So it's really not that complicated intuitively. Of course, the devil lies in the details, but intuitively that's what the circuit is doing, which is was pretty interesting to put all the pieces together. I hope that was helpful, and I really will try to do an example with a simulator. Hopefully that's easier to do. And it might take me a couple of videos, but I think that can be probably really illustrative. Perfect.